All right. So now what do you want to discuss? I mean, if you have gone through that chapter, which is chapter 13, it is actually completely straightforward. It's just a lot of calculations. But the concepts are all completely straightforward. Whatever you have learned in general, I mean, the notion of the roots and all that, you just have to apply it for the SUN, SON, I mean SO2N and SO2N plus 1. They behave very differently. SO2N and SO2N plus 1 behave very differently. Which is also clear from the linking diagrams we saw, right? The BN series was an odd SO2N plus 1, whereas the DN series was an SO2N. So they are very different in terms of the behavior. And then finally SPN. So all of these things are worked out. It is just a matter of, in fact, most of it is exercises. So, so you just have to go through that. So either I can do a little bit of that, or I can just move on to spinor representation. So this way. So I mean that's not included in the course, but I think that's for a physicist. I mean, particularly for us particle physicists, I mean, spinors are very important. So it's useful to know. I mean, we have not included it in this course. So it will not be, there will be no exam on that. I mean, exam will not ask no questions on that, but it's just a matter of knowing it. Spinor representation. So any opinions on what we should do? I don't know. This is basically, it's just a matter of sitting down and working on it. Maybe it will take you half an hour or so to go through it. So all of them is chapter, 13 chapter. You know, finding the roots for the SUN in general, finding the roots, then the inner product between the different roots, and you'll find that all the roots. And then find the, you know, now we also know about the positive roots and simple roots. This was not discussed in chapter 13 because the concept of positive and roots and simple roots was discussed in chapter 14. No? So if you include also that knowledge, you can immediately work out what are the positive roots. I mean, you can you have to choose some regular element, regular element of the kata, because depending on what you choose, you have the set of positive roots. Different choices do not matter. You just choose one of them and one regular element. And with respect to that, you have a definition of positive roots. And once you have the positive roots, you find what are the simple roots. Okay. So the number of, that is not here. In 13.2, for example, let's say SUN, 13.2, section 13.2, you start from the Karma subalgebra. Okay, let me just do the SUN very quickly. And then you go through the SO2N, SO2N plus 1, and SPN. Later on, after your exam. And then on Wednesday, if you have any doubts about it, you can go through that. Plus other things. Okay, so SUN. So what we have SUN or SLN, because we have anyway complexified. Once you have complexified, there is no difference between SUN complex or SLN complex. Okay. So that is why in the notes many times the language which is used SLNC. Okay, but I will keep using SUN because really what we're interested in SUN. So either SUN, I mean complexification of that, or this is the same as SLN. So here what we have is all the traceless matrices and biomatrices. Right? I mean, let me just mention this. So what is the point? I mean, take SU2 for example. Let's take SU2. In SU2, what you have, the way it's defined, it is a set of all traceless Hermitian matrices. Right? So that would be sigma 1, sigma 2, and sigma 3. I mean, generated by any such traceless Hermitian matrix can be expressed as linear combination of these three. Linear combination with real coefficients. So you have, so arbitrary element will be some A sigma 1 plus B sigma 2 plus C sigma 3, where A, B, C belongs to real numbers. That is how, that's SU2, yeah, right? But so therefore, now if you look at this here, sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I 0. And sigma 3 is 1 minus 1, 0, 0. Now, if you allow this to be complex numbers, then you see there is no, you can just get arbitrary numbers here and arbitrary complex number here, right? So if you suppose A, B, C, now you make them to be complex, belong to complex numbers, then the matrix that you will get by taking arbitrary combinations, A sigma 1 plus B sigma 2 plus C sigma 3, where A, B, C are arbitrary complex numbers, will just become arbitrary complex numbers, Z1, Z2, Z3. These are complex numbers, but it has to be traceless. The trace condition doesn't change. Even if you multiply this by complex numbers, the trace is 0, trace is 0, trace is 0. So all the trace is 0. So this will be minus Z1. But Z2 and Z3 are completely arbitrary. Whereas if you do it like this, I mean, if you take it to the real numbers, then you see, if you look at this combination, what you will get, that combination will be A minus IB and A plus IB. Which means these two are complex conjugate of each other. But once you allow A and B to be completely arbitrary complex numbers, then this and this are totally independent. This is one complex number, that's another complex number. So that's why it becomes like that. Whereas before, for the SU2, you had the structure, this is some real number, x minus x, and some z bar. Right? That was for the SU2 with the real emission matrices. But once you complexify, it just becomes arbitrary complex numbers, but traceless. Because this is now arbitrary complex numbers. A itself is, say, A1 plus IA2. B itself is B1 plus IB2. No? So these are arbitrary complex now. Now we are considering complex. Here it becomes A1 plus IA2 plus, minus. So this is minus, and this is minus. And here it is plus B1 plus IB2. Now look at the real part here. The real part here is A1 minus B1. That's the real part of this. And here the real part is that. Here the real part is A1 plus B1. Clearly these two are independent. You can choose arbitrary. No? I mean, call this is X1 and this is X2. These are independent completely. There's no relation between them. No? And similarly, if you look at the imaginary part now, here it becomes I, so A2 minus B2, whereas here it becomes I, A2 plus B2. Again, these two are independent. That's why that's the reason why once you complexify, it becomes arbitrary complex numbers. Z2 and Z3 have no relation. They're independent. But this is the same algebra as that of the SL2C. SL2C. It's the same algebra. SL2C is arbitrary complex numbers, but just traceless condition. That's all. Because SL group, at the group level, SL, the determinant was 1. That translates into traceless condition for the infinitesimal generators. That's all. There's no other condition. These are all arbitrary complex numbers. So that's why one says that SU2, once you complexify, that's the same as SU2 complexification. Here I was considering real. This is the same as SL2C. And the same thing happens for SLN. SLN versus SUN, once you complexify SUNC. That is the. So that's why in this entire thing, usually one uses in the notes, we use the SLNC. But once you get the algebra after complexification, right, all the roots and everything else, then you restrict to the SUN real by imposing conditions on the parameters. That's the way you get SUN from there. Anyway, so for this, so SLNC would be simply any matrix, any n by n matrix, with just trace equal to 0. That's all. There is no other condition, right? So I can choose a basis. For example, I think, yeah, what was I calling? We were calling EIJ, right? EIJ were the matrices which was the only non-zero entries in the ith row and jth column, right? I think this is, or was I calling XIJ? I think it was EIJ. Right? So EIJ is nothing else. EIJ KL. So this labels the matrix. This is not the row and column. This is just the name of the matrix. But I put this index ij because there will be as many matrices as I and j. So this is an n by, this whole thing is an n by n matrix. And now if this matrix, if you look at the entry in the kth row and lth column, is nothing else, is just delta ik, delta jn. That is the way we define. So you'll have the basis for, this will be the basis for arbitrary n cross n matrix. But now we have to impose a traceless condition. Okay. So that means the only condition here, off diagonal terms are completely arbitrary. I mean, I can just choose everything 0, everything else 0, just say, for example, this. This is perfectly okay, everything else 0. Yeah. So this will be like, this will be E12 matrix. This will be the matrix E12. Because the only non-zero entry is in the first row and the second column. Right? However, for the diagonal one, we have a constraint. The constraint is that an arbitrary matrix, so arbitrary matrix M will be, okay, let me just write it like that, xi, mi, or even zi, mij, eij, sorry, eij, for I not equal to j. So that is where these are arbitrary complex numbers. But for the diagonal, we have a condition, zii, eii, summed over I, but these have to satisfy the condition sum over zii, I equal to 0. That's a traceless condition. Because eii are the diagonal. Eii means just the ith row and ith column is not 0. So that means in this matrix, if you let's write down what is the matrix here. This matrix will be Z11, Z22, Z33, and the off diagonal will be Z12, Z21, and so on and so forth, right? But now we have the traceless condition. So sum over these guys must be equal to 0. Okay? That's what it is. So our basis we can choose for the karta. So now what are the steps? We have to first choose a karta, a convenient karta, something which is convenient. Convenient to compute do all the calculations more easily. So the natural candidate is just the diagonal matrices, just like we did for SU2 and SU3. No, we just chose the diagonal matrices as the karta. So this will be just the EII. Okay. So let me see. So H, so let's say arbitrary karta subalgebra will be just given by H equal to HI EI. Huh? Okay, EI I will define, where EI is nothing else but EII. So HI, EI, sum over I, 1 to n, but with constraint, because you have to have a traceless condition that sum over HI equal to 0. So this is the set of all the karta. This is a subset. This is the subalgebra, karta subalgebra. So it's just a diagonal. Put all the off diagonals 0. And then this is what I'm calling Z, H1, H2, etc., etc. And the only condition is sum over HI is equal to 0. That's the condition. Now, what about the roots? So then you use this, if you take the commutation relation of H with EIJ, arbitrary H, satisfying, of course, this condition, with EIJ. So EIJ is a matrix which has only non-zero entry in the ith row and jth column. And you find, I think this we have done before already, you will get HI minus HJ EIJ. Right? I mean, it's easy to see because if you think about it, H is diagonal here, right? H1, H2, etc., etc. And Eij is the only non-zero entry is in the ith row and jth column, and that's 1, right? Everything else is 0. So when you take the commutator, I have this times that minus that times this. I will take the two orders. When I take this times that, the only so in order to get this thing, I should have I mean this row will multiply the columns, right? So here, I mean when it multiplies these previous columns, of course everything is 0 because the whole thing is 0. Similarly, later columns also everything will be 0. But this column is the only place where you will get non-zero. But that means it must be in the ith row. Jth row, right? Because this jth row will also the non-zero entries in jth column. So this will multiply and will give you something non-zero. So you will get, how come? Here we have hi minus hj. This is equal to hi. Okay, let's see. Maybe I'm making a mistake. Eij. Ith row and jth column. According to this argument, it should be minus. No? You know, let's see. Have I made a mistake here? So if I take the ith row, I mean ith row. No, but that's not possible. Ith row and jth column. No, I think this is a mistake here. It seems to me it's hj minus hi. Yeah. Let's see again. So what do you say? What is your opinion? Is it hi minus hj or hj minus hi? I mean, take the simple example. Suppose here I is 1. So I say 1. The only non-zero and say j is n. So we are looking at I equal to 1 and j equal to n. So that means only non-zero entries in the last one here. No, this is okay, right? So hi minus hj. Sorry?
hi is in the first row.
Hi is in the first, h1 is in the first row.
Yeah.
So that's correct. So this is correct. Correct. So yeah. One and yeah, correct. So this is the formula. Okay. Now, so those are the roots, non-zero roots. I mean, clearly for, of course, I equal to j, this is 0, because that's the component, so that's 0. Okay. So now, the trick, okay, so we want to go to the dual space. To find the roots, we want to write the roots in a convenient way. You remember, we have to go to h star. So the dual vectors, just like we have chosen the basis EI. EI is not, I mean, this is because there is a constraint here, right? Sum over HI should be equal to 0. So it's not that all the EIs are there. Okay. So really, I mean, not all the EIs are there. You see, you cannot have just a situation like you have H1, E1. This is not an element of H. This is not an element. You can have H1, E1 minus H times E1 minus E2. That is okay. That belongs to H. Because now you have the piece of traceless. Right? Okay. So that's not. So it is not that so you don't have the basis. I mean, EI does not belong to H. Okay. But if I take any combination with the sum of it is equal to 0, that belongs to it. So if I choose all the EI as a base, that is too much. That's bigger than the H space. Okay. However, nevertheless, sometimes it is convenient to go to the bigger space, but always impose the similar constraints. See here, I'm using the bigger. I started with the bigger space where I take all these basis EIs, but not all the EIs belong to not arbitrary combinations of EI belong to H. Okay. So we'll do the same trick for the H star, and we'll define a basis for this. H star a basis for H star. and we'll define as omega I, okay, where with the condition, so let me write it like this. Again, some AI omega I, where AIs are sum over AI is equal to 0. That's the condition there. And omega I itself is defined, so omega I belongs to some dual vector space. And omega I is defined as this acting on EJ is equal to delta EJ. Remember, the dual vector space contains elements which are basically linear functions, which map the vector space to numbers, to real numbers. Right? So I define this basis omega I in a bigger space, first of all, not in H star, in a bigger space, which is dual to the bigger space, the n-dimensional space generated by EI. So we start with some vector space V, which is n-dimensional. Its basis is EI. Okay, but not all of, I mean, V is bigger than the H. Okay, so H subspace is contained in V, is a subset of V, and is defined by precisely this condition. So V is defined by arbitrary. So V is defined by HI, EI, summed over I, but no condition on HI. HI can be arbitrary. Okay. So this V is a bigger space. H is a smaller space. H is contained subset. H is subset of V, where the constraint is that HI should satisfy this condition. Okay. So what we do, we started with this big V space, and then go to our Cartan subalgebra. And here again, in the dual thing, what we're doing is that we go to the dual vector space, V star of this, and then go down to the H star, which is contained in V star. So this is the idea. So with this, so we can define this. We can define a basis. This basis is omega I, where omega I is simply defined. In order to specify this basis omega I is of course a linear function on this vector space. So we define the linear function to be simply that. Okay. So in other words, omega I acting on Hj, Ej, summed over J will be simply Hi. So from this, use this formula, and you get that. So this defines to you a unique function, linear function. Okay, so we'll work with this basis omega, which is actually in the V star basis in the V star, not in H star, basis in the V star. But it's convenient to work with that. This happens for basically only for SUM. When you look at the other examples, SO 2Ns, SO 2N plus 1, SPN, you don't have to go to this bigger space. Here it's just bigger because you want to deal with that traceless condition at the end. Okay. In the beginning, you just work with the situation where the tracelessness condition is not there. Okay. But then you impose it as a constraint. All right, so if I define it like this, then you see from here, it immediately follows. So what is this guy? I mean, this is nothing else but, so if I write it as, so if I write this commutation relation as, I mean, this commutator as sum over Hi, Ei, commuted, this is an element of H, this belongs to H. I mean, to begin with V, if the sum over Hi is equal to 0, it belongs to H. Commuted with Eij, let me put here, K, Eij, then that is nothing else but, call this H. Okay. Then that's nothing else but omega I H minus omega J H. Because you can see that, I mean, omega I H by definition is nothing else but, I mean, from that definition, this is nothing else but Hi, that is Hg. And we see that that's exactly the answer here, right? I mean, this times Emg. Right? When we took this commutator between this and that, we found it is simply Hi minus Hj times Eij. So this one, we want to write it as the usual notation, alpha H, no? Alpha H. So the root here, so therefore the root here, the corresponding root alpha ij is nothing else but in this basis, in the basis we have chosen here, in this basis it is simply omega I minus omega j. I mean, just write this as alpha h. Alpha is in the dual vector space, and we have chosen a basis for the dual vector space omega I omega j, so it's omega I minus omega j. So those are the roots. Okay. Okay. So basically, all the roots. So you can see how many roots are there. The roots are, when I is equal to j. Of course, this is 0, but that we knew. I equal to j just means eij. If I is equal to j, this is a diagonal element. That's Cartan generator. That's part of the Cartan. So the commutator is 0. Root, I mean, the eigenvalue is 0. But anything else, when I is not equal to j, this is not 0. Okay, so that does the job there. Okay. So therefore, so if I write in our usual notation, the space, the subspace of the full algebra, which is characterized by alpha being omega I minus omega j. Nothing else but the complex numbers times eij. So that is the root vector. That's the root vector corresponding to the root omega I minus omega j. And that's a one-dimensional subspace. Now, again, you can do the same thing. Now, let's compute B of HH, the Cartan form. So what is B of HH? The definition, of course, we know it's simply sum over all the roots, alpha h, alpha belong to the roots. So the space delta is nothing else but omega I minus omega j for I not equal to j. For I not equal to j. In the notes, what we have done is that we have just chosen a convention, well, not convention. What we did, I mean, when I is not equal to j, there are two possibilities: I greater than j or I less than j, right? Two possibilities. So what we have done is we have not to. So if I take I less than j, so yeah, I mean, you can just restrict, right? Because if I take the other way around, I'm just going to pick up an extra minus sign, right? So if I just exchange I and j, you're just going to get omega j minus omega I, which is minus of that. So there will be always a positive root and negative root, that we knew anyway, right? So that is the way. So one can also write it like this. This is the same as omega plus minus omega I minus omega j with I less than j, or I greater than j. Choose one choice. So this is the same, right? Okay. So in the notes, you'll get it like that. Okay, so now we want to do this here. Well, this is nothing else but since alphas are just always omega, I mean, let me go back there. Omega I minus omega j h times omega I minus omega j h, right? Summed over all the roots where I is not equal to j, right? Here is I is not equal to j. So I'm using this language instead of writing as a plus and minus. So that's what it is. But omega I, so what is this? This is nothing else but hi minus hj here. And similarly this, so this is a square. I not equal to j. Okay. So let's open that up. So this is the same, this I sum over I not equal to j, hi square plus hj square minus 2 hi hj. Minus 2 times hi hj. But we have a constraint here, right? The constraint is that the sum over hi, I mean, we are not working in we are actually working in the H space, the Cartan subalgebra. There, there's a condition. The sum over hi is equal to 0, tracelessness condition. So we have a condition that sum over hi is equal to 0. Sum over hi equal to 0. So we have to use that to simplify this expression. So let's see how we simplify that. So I can use this constraint. So then this means of course the sum over hi whole square, sum over all hi whole square should be equal to 0. If sum over hi equal to 0, then square of it's also 0. But then I can open it up. This is the same as the sum over ij hj. Right? I mean sum over hi times sum over j hj. Square just means that, right? So I'm just rewriting together. So this I can split into two parts. One when I is equal to j, and other remaining part when I is not equal to j. So one term will be sum over hi square plus another term when these two are not equal. I and j are not equal. So sum I not equal to j hj. Right? Okay. So therefore this becomes, yeah. So let's work it out then here. So first term, so this I will use to simplify that expression. So this whole thing is 0. So therefore sum over hi is simply minus sum over hi square. Now let's do the sum here. So this is, let's look at the first term. So we have hi square sum over I not equal to j. But how many, I mean, but see, there is no j dependence here. I mean, so this is really what it is. It is j, sum over j, but j not equal to, there are two sums, I and j. I have to sum over I, and I have to, so maybe I should do first here. Sum I and sum j, j not equal to I. That's what it means, right? When I write something like this, I not equal to j means I have a sum over I and j both, but I have to remove the I equal to j term. No? That's what it means. So this, I can write it like this, but this, I mean, if you look at that, I mean, here there is no j dependence, right? So I can sum over j easily because there's no j dependence here at all. But how many terms are there where j is not equal to I? That is exactly n minus 1, right? I mean, say I is 1. Then this sum is over j, all j, but j not equal to 1. That means 2, 3, 4, up to n. So n minus 1. So this is nothing else but n minus 1 times hi squared. Okay. That's that. And the same thing happens for this guy. Hj square, again, write the same thing. Hj square, sum over, now I just do the j sum. I mean, first I sum, but, and then the j sum, but I should not be equal to j. So first I fix a j, sum over I should not be equal to j, and again it's the same thing, obviously. So it's n minus 1, sum over hi square. J square, but that's the same as sum over hi square, let me say. Okay. So these two terms give you n minus 1 plus n minus 1. So it's 2n times minus 1, these two terms together give you sum over hi square. Okay. But this term gives you just this last term here. 2hi hj, by using this equation, just gives you, I mean, this is simply minus hi square. I mean, this is equal to 0, right? So this guy is minus hi square. So therefore, 2 times that is minus times minus. So 2, plus 2, right? So that will give me plus 2 hi square. So altogether, this result is simply 2n. 2n times sum over hi square. because this 2 cancels with the -2, and you just get 2n. So that is the BHH. Yeah, so I don't know if you remember this, we always defined a factor. I mean, one of its earlier chapters, no? What we were calling CG. I think in one of the earlier chapters we would use that. You remember that this convenient factor here. So this was the there was a convenient factor which we used in page 77. In page 77, we defined page 77. There's the equation alpha k is equal to some constant CG. This is the group, or Lie algebra that we're talking about, times B of H alpha K. So that was the definition. Given the root, we wanted to define a mapping from the H star to H, a map. This is a map. So this defines to be a map. See, once you have the metric Cartan-Killing form, you can go from dual vector space to vector space. Define a canonical map. This was a map, and that is done via this Cartan-Killing form. So you say that for every k, alpha k is equal to b of some element, h alpha k. That element is what is alpha maps to. But in that definition, we had an arbitrary constant here. That constant was just depending on the Lie algebra you talk about. It's not important really, but it was convenient. And in fact, there is written there somewhere that for SUN, actually in that same page 77, is also written SUN. For SUN, it's convenient to take CG is equal to 1 over 2n. And the reason for that is this. I erase that. No, here it is, right? This 2n. Yeah. So we just wanted to get rid of this 2n. That's all. It has no, no fundamental reason. It is just to make it more easier, not write shorter form. Yeah, nothing other than that. Okay. So for SUN, you choose this. So therefore, then what we are saying. So if I take this alpha, so let's take the alpha to be. We know that the set of roots are this omega I minus omega j. So if I take alpha equal to say omega I minus omega j, then we want to ask what is the h. So the question is, what is h of omega I minus omega j? That's the question you're asking. No? So which element of the Cartan this gets mapped to? That's the question. And the formula is here. So what we can do then is to use this. So CG is now 1 over 2n. So this is 1 over 2n. Okay. So we want to find now what is h alpha. So let's go back here. Right. So let's say, so we apply this to some arbitrary k. So we are looking at omega I minus omega j acting on some k, where k is of course an element of Cartan subalgebra. So it is in general some KL, EL, right? With the subject to the condition that sum over KL is equal to 0. That's the condition. So that's an arbitrary element, k. I just expanded on the basis for the Cartan. So this should be equal to 1 over 2n and b of h alpha, h omega I minus omega j, comma, sum over k or EL. So we want to find this h of omega I minus omega j. Well, this is an element of Cartan generators. Cartan subspace. So I can again expand this in terms of the basis, no? In terms of the basis here. So let's write h of omega I minus omega j is equal to some numbers. Let's call it h of L omega I minus omega j here. Okay. Since it is an element of the Cartan, I should be able to write expand on the basis. So if I can, so our aim is to determine this coefficients. If I know these coefficients, and I know what h omega I minus omega j. Okay. So where was this formula? Yeah, so maybe I should write it down somewhere. BH. This is an exercise problem. Actually, I should have. There is an exercise problem down there. Exercise 13.1. Just like we proved that B of HH was 2n. This was the proof given here, sum over HI squared, where H is nothing else but HI EI. So the coefficients are there. This was the proof. This sum over I. Similarly, there's an exercise here, exercise 13.1, where you have to show that B of, this was the same element, HH, no? Now we want arbitrary elements, B of H comma K in a product. That exercise is asking you to prove that that's the same as 2n summed I equal to 1, I mean I and sum over I and K, now sum over I equal to 1 to n, HI, KI. Okay. This is a statement that you need to prove. Okay. Where again, this proof is again based on that similar thing that we used for the previous proof. You know, because when you write down, I mean, okay, let me just give you some hint. So this will be again, what will be this of course will be sum over alpha H alpha K, right? Sum over alpha. This is the definition of the Cartan filling form, right? But then again, this is nothing else but omega I minus omega j on H and omega I minus omega j on K, summed over I not equal to j. Okay, I mean the same thing. And but this guy will be, this will be HI minus HJ, and this will be KI minus KJ. Okay. So once again, so you will get, so if I open this up, I mean this HI and HJ have this expansion coefficient. So if you write H is equal to HI EI and K equal to KI. KI EI. Okay. These are the coefficients. So omega I minus omega j acting on H will be simply HI minus HJ, and this acting on K will be KI minus KJ. No? So this will be, this will have several terms, HI KI plus HJ KJ minus HI KJ minus HJ KI, right? And summed over I not equal to J. And you have to again use the same thing that this is traceless. So in other words, there's a condition that sum over HI and sum over HJ, KJ is equal to 0. Like before we use the condition that H is traceless, or sum over HI whole square is 0. Now we can use, now we have to use this condition, I mean this equation, that the trace of H is 0 and trace of K is 0. So sum over HI times sum over HJ should be equal to 0. So this will give you a condition on the cross terms, HI, KJ. And you use that to simplify this, okay? And finally prove this formula. This is the exercise. Is that clear? So it is just using the constraint that these are traceless. So because of using that constraint, you get some relations. You can express again these cross terms, HIKJ minus H plus HJKI, back in terms of the terms which are involving the same index, HIKI and HJKJ, by using this traceless condition. I mean, try that out. I mean, that's an exercise. So if you use that, the result of that exercise, Then you find that this, okay, so, right, so if you use that result, then, and let's write it like this, H omega I minus omega j is that, then this formula, that formula just gives you, it's HL KL, H omega I minus omega j KL, sum over L. 2n cancels. That is the reason for that. This 2n cancels with 1 over 2n. So you just left with that. You see what I'm saying? So this is arbitrary k. Arbitrary k, I can expand like that, KL. This one, I expand like this, and my aim is to determine these coefficients. Because if I determine this coefficient, then I know what that is. So I substitute that there and use this formula. BHK is that. Okay. So it is the diagonal sum of the coefficients, right? The coefficient of the k, I mean the ith coefficient of k, ith coefficient of h, and it's a product and the sum it up, right? And here, we are just looking at the Lth coefficient is KL. Here, the Lth coefficient is what I call HL. This is a number. This is some number, and our aim is to determine a number. So that's what it is. Okay. But on the other hand, I know what it is. I mean, omega I minus omega j acting on that is simply ki minus kj. Okay. So this result, this sum is equal to that. So this guy is equal to that. So that means in this sum is over everything, the only non-zero terms will be when L is equal to I and L is equal to J. And when L is equal to I, this coefficient is 1, and when L is equal to J, the coefficient is minus 1. That means HL omega I minus omega j is nothing else but delta Li minus delta Lj. Right? So when L is equal to I, this coefficient is 1. And when L is equal to J, its coefficient is minus 1. And for all other values of L, it is 0. So HL omega I minus omega j is that. And now you go back here, then you see that this is nothing else but EI minus EJ. Right? Because only when L is equal to I is plus 1, so you get EI. And when L is equal to J, it is a minus 1, so you get minus EJ. So this is the relation. So what is a nice thing that the dual, I mean, this guy maps to what we call H alpha, but that H alpha is nothing else but EI minus EJ. So it's a very simple formula. If you had not divided by 2n, there will be unfortunately these 2n's floating around here. It is just to remove that. One has to use this thing. Ultimate results do not change, I mean, because as we said, the fundamental results are always involving the ratios of this Cartman form. So it doesn't matter eventually. Those 2n's will cancel. So that is the, yeah. And final thing is, so once we have this, remember that in that chapter, I don't know, I erased that page number. That chapter, we also, there were 2 steps. One, by giving the Cartan-Killing form, we have a map between the dual space to H from using the Cartan. So for a given element of dual space, I can define a unique element in the space, right? But then I can also, so what was it? You say B was actually defined here. This was the metric in the Cartan subspace, right? But using that metric, I could give a map between the dual vector space and vector space. But we can do one more step. We can use this definition to define a metric itself here, some metric on the H star itself. That is what we were denoting by, I mean, that's why, so we were denoting it this procedure like this. So first we have this B of HK, H and arbitrary element of the Kaplan subspace, H and K, this is a metric. Then we use this definition to define a map alpha to H alpha. Right? And then the next step was we also defined a metric on the, so this was an H star, so this belonged to H star, and that belonged to H. Right? And then the last step was we used this definition to define a metric, alpha beta. So these are alpha and beta belong to the alpha beta belong to H star. And we define it simply as B of H alpha, H beta. Because I have a unique map. Alpha is mapped to a particular element, beta is mapped to, again, a particular element. And I define the inner product of this as simply the inner product, which is defined here in this space between H alpha and H beta. Okay. That was the definition. That was the way to define. So the last step was, so we can, using this now, you see, this was the map. We said this H omega I minus omega is nothing else but E. So omega I minus omega j is mapped to that. So if I want to look at alpha dot beta, so if I want to look at the alpha dot beta, so let's say there is a alpha. So alpha I take it to be omega I minus omega j. And beta is again or something of this form, but in general some omega k minus omega L, right? That will be the another root, omega k minus omega L. So I can define alpha beta as simply the H alpha B H alpha. Again, there is a 1 over the 2n factor for convenience, B H alpha H beta, right? But that's the same as H alpha is E I minus EJ, right? This is mapped to EI minus EJ. And this is EK minus EL. And that, so, I mean, this we already computed, right? BEI. So this we already know. B of HH. So B of HH, arbitrary, was simply sum over HI square, right? 1 over 2n. So there's a 2n here, and that 1 over 2n cancels. So we just have that. So we can see B of HK, in fact, let's say HK. In fact, that was the exercise problem. It is nothing else but 2n HI, H, let me put, not use IJKL, HM, KM. Summed over n. Summed over n. That was the exercise problem. So n is going from 1 to n. Okay. But now we are looking at a particular h. H is simply, so m is delta im. I mean, hm is delta im. So this is 2n delta im minus delta jn times delta km minus delta lm. Okay. Summed over n. That's a term. So what I did, this is a general term, right? HK, this is a general expression, but now we specialize to the case. I take H to be this guy and K to be that guy. Okay. But that means the M, I mean, this M is not, I mean, this is HM is not zero only when M is equal to I and J. When M equal to I, it is +1. When M equal to J, it is -1. Right? And similarly here, the same thing for the K. Unfortunately, this K, I shouldn't, maybe I should call it H prime. H prime. So this is H prime. Okay. So H prime, on the other hand, is this element. H prime, this M is not zero only when M equal to K or L. When M equal to K, it is +1. When M equal to L, it's -1. So that is what I've written here. Delta IM minus delta JM for the first guy. And the second guy is delta KM minus delta LM. Okay? Chronicle delta. Now you just multiply that and sum over it. So we can sum it up. And the result is, so there are 4 terms here. So if I sum this up, the delta, so there is a delta IK, okay, and minus delta IL, minus delta plus delta JL, minus delta LI, delta LI. Okay, this is the result. So we are saying that the inner product of omega I minus omega j with omega k minus omega L is equal to that. This factor of 2n cancelling with that 1/2n. So that's just simply that.
Professor, can we define a dual vector space for any given vector space?
Repeat that again.
Can we define a dual
Dual vector space for any vector space. Yeah.
Sure. Yeah. So, okay, the inner product of any dual vector space cannot be defined without a metric, but the limit of a dual vector space or vector space can be.
That's always different. Yeah. Sure. Yeah. Because that's in that definition you never use the metric at all. That definition is given by simply linear functions. So there's a linear map from the vector space to real numbers. It has to be linear though. I mean that is the important point. That is why
it cannot be it can be not linear.
No. So this is not for, this is only for linear. Of course, you can make some non-linear maps, but that will not define your dual vector space. For example, let's say the dot product of 2 vectors. That is again, it maps let's say the length square of a vector. It's a map. It maps the vector space to real numbers. No, actually, even positive numbers, non-negative numbers, if it's a metric is positive. But that is not linear. Here we are talking about only linear numbers. There's a linear map between them.
So the inner products and the vector balances in the dual vector space or the vector space needs a metric tensor to be defined, right? There must be a tensor to define.
Yeah. So the metric is, I mean, the vector space itself is a concept before you were talking about the metric. Then you can start adding more structures to this abstract object, so vector space. So the additional properties that you use, additional properties you define are, for example, the metric. So that one has the concept of length and the inner products and so on. But to begin with, at the very basic level, vector space is just a vector space where there is a standard definition.
So we can deal with the vector product or the lenses and the vector space without defining any metric, right?
Vector product.
I mean, like the dot product. So the dot product.
Dot product is a metric. By definition, right? Because once you define the dot product, which is obviously bilinear in the 2 arguments, that is exactly the metric. Because once you choose a basis, then the metric you can write it as a, say, suppose an n-dimensional space, vector space. If you choose a basis, say EIs, then once you specify EI dot EJ, then you find the Of course, there are some conditions on metric. It should be bilinear map and it should be symmetric. So EI dot EJ is the same as EJ dot EI. So there are some conditions, basic, I mean, yeah. Okay, so now this is the inner product. Okay, now you can see here. So if suppose I take the length square, I mean, so in other words, let's take alpha. Okay, where alpha is omega I minus omega j. But so say alpha equal to omega I minus omega j. But remember, this is I not equal to j and k not equal to L, right? That is when you have non-zero roots, and I is not equal to j and k is not equal to L. So take I not equal to j here, that's a non-zero root. I want to find what is the length. So that is the same as omega I minus omega j omega I minus omega j. Okay. So you will get, now if you substitute that here, you'll get a delta II, no sum here. There's no sum here now. This is a particular I. So you get 1 from here, 1 from there, right? But the off cross terms are 0 because we are saying I is not equal to j. So you don't have a, I mean, delta ij is not there. So this is 2. So all the roots, all the non-zero roots have the same length. No, root 2. That's this was so. What this is what we saw in SU3, but this is completely general for any SU. All that. And furthermore, okay. So this is one thing. Now let us go to the say the concept of so positive roots. Okay. So for the positive, so we have to define, right? All the roots are this omega I minus omega j. So we can choose some regular element in the Cartan to define this what is the notion of positive roots, right? So let's see. So we can just choose the same thing that is defined here. Yeah. So choose the Cartan element to be so general Cartan element is HI-EI, right? That's the general Cartan element with the trace being equal to 0, sum HI equal to 0. This is in the Cartan, general Cartan element. Okay. But now let's choose a regular element. There's an infinite number of ways of choosing regular elements. It's not just one way, but choose one thing. Choose one of them. So we choose H0 equal to sum over HIs, sum over HI, EI, but with a condition we choose H1 greater than H2 greater than Hn minus 1. Greater than HN, sorry, greater than HN. Okay, so I can just order. So this, remember, these are just the EIs for the diagonal. So as a matrix, this is nothing else but H1, H2 up to HN. Okay. This is what matrix is. With this traceless condition is that sum over H this is equal to 0. Okay. Now we choose a particular ordering. We say that H0 is a particular element which has this property that this is greater than that, that's greater than that, and so on. That's an H0. Okay. So with that definition, you see, it will never be 0. For any root, the root, for any root, if you take any root alpha, so we want to look at alpha H0. We want to check whether this can be 0 or not, right? Regular element was defined as something which so this is not going to be 0. That's what we want to check. So what is this? So let's take alpha equal to omega I minus omega j. All the alphas are of this type, right? Where I is not equal to j. So take this alpha to be that. For a generic I and j, it doesn't have to be some specific I and j. This is nothing else but H0 of I minus H0 j. Right? This H0 is, HI and j. H0 I'm taking it to be this. This is H0. So it is simply HI minus Hj. But with this condition, it can never be 0. Right? None of them are equal to each other. And in fact, there's an ordering. We have given even an ordering. But first of all, we see that none of them is equal to each other. So this can never be 0. Okay, maybe I can put here a subscript not here. So this is not. That makes it more clear. So this is a particular element. I call it H0. So alpha of H0 is nothing else but that. Okay. But none of this, for I not equal to j, this cannot be 0. So therefore, H0 is satisfying our condition, our definition of a regular element, right? For none of the roots, it is 0. For none of the non-zero roots, it is 0. I mean, alpha H naught is 0. So with that condition, now you can see that what are the positive roots? Positive roots for this is so we call all of those roots positive such that alpha H naught is positive, right? And those roots alphas for which alpha H naught is negative, we call them negative roots. That was the definition of positive and negative roots. So according to this, we see this will be positive if H naught I is greater than H naught J. But with this ordering that we have put, that just means I is less than J, right? If I is less than J, then that is, so that means the set of positive roots, delta plus, is simply omega I minus omega J for I less than J. That's the set of positive roots. And of course, the negative roots are the other one. Delta minus is omega I minus omega J, where I is greater than J. That's the negative roots. Now, so let's explicitly write down. So these are, okay, so now the next step is what are the simple roots? Okay, we have the set of all the positive roots. Now we want to find out what are the simple roots. So remember, simple roots were what? They were the ones which could not be expressible, could not be written as sum of two positive roots. No? And that is, so I just write down the solution answer. So sigma, the simple roots, is nothing else but omega I minus omega I plus 1. Omega I minus omega I plus 1 for I going from 1 up to n minus 1. Any other root can be expressed. For example, so what we are saying, that means, I mean, so this is basically omega 1 minus omega 2, omega 2 minus omega 3, and omega n minus 1 minus omega n. Okay? So this is what the set of simple roots is. There are n minus 1 of them. The rank of SUN is n minus 1. So you should expect the number of simple roots to be same as the rank of the dimension of the Cartman-Cell algebra. So it's n minus 1. And indeed, you can see, for example, if I take the sum of these two, I will get omega 1 minus omega 3. So omega 1 minus omega 3 is not a simple root. So it's only the adjacent ones. See, 1, 2, 2, 3. No? Anything else, omega 1 minus omega 4, I can write it as this plus that plus the next one. So omega 2 cancels, omega 3 cancels, and you get omega 1 minus omega 4. No? Or if you want omega 2 minus omega 4, you just take omega 2 minus omega 3 plus omega 3 minus omega 4. No? So everything else can be expressed as that. And this cannot be written as any sum of any two positive roots, each of them. So that's a simple root. Okay. And now let us compute the so now let's look at this. The last step was to compute the Cartan matrix elements, right? Cartan matrix elements. Remember we found what was that? Cartan. I think you were calling Aij was equal to 2 alpha I dot alpha j over, I'm not sure whether alpha j or alpha I alpha I. There was a alpha j, yeah. Okay, so if you look at these numbers are all, so we can compute, so what are these are simple roots, right? So the simple roots are this. So we are looking at the inner products of this, right? So for example, if I look at inner product of this, okay, first of all, we know the length squares are all 2. So length square of all these are 2. I mean, that's 2 for every root. Yeah? This is generally true for every root. So in particular also for the positive roots and negative roots, and in particular for the simple roots. So all of them are length square 2. Now let's take the, so let's say I take omega I minus omega j with omega I with omega I plus 1, we are looking at a simple root, and omega j minus omega j plus 1. We look at that. Okay. So this will be, so you get I, so you get I with j. In fact, let me make it like this simple. 1, 2, and let's say first of all, 3, 4. Omega 1, so this is the 1, 2, the first one, with omega 3 minus 4. That is clearly 0 because you see there is none of this Kronecker delta will be non-zero. I mean delta 1, 3, delta 1, 4, delta 2, 3, delta 2, 2, none of them. But, and so on. So anything, so let's say put here j plus 1. This will be 0 if j is not equal to 2. Right? I mean, for j equal to 1, it is for j equal to 1, it is just a norm, which is we know that is omega 1 minus omega 2 square. I mean, that's a length square. So we want to look at two different roots. This is anyway 2. That we already know. That's in general true. So what we are looking at is two different roots. So j cannot be equal to 1 because I'm looking at the first one. So j can be 2, 3, 4, 5, etc. If j is equal to 3, etc., there is no common numbers here. No? So it's all 0. So only for j equal to 2, you find. So for j equal to 2, now what happens? This will be omega. So the only non-zero term is this Kronecker delta 2j, because this is 3. 3 is not equal to any of these numbers. No. So you get a minus 1. Okay. So the structure is this. So if I and this will be true for anything. I mean, if I take, say, j, if I take I plus 1, and let's say I is less than j. Okay, anyway, this is symmetric, right? So even if I was greater than j, I can always arrange it to say that one of them is less than the other, and not equal. If it is equal, then the length square is 2. So we don't care. So I is less than j. Then the only possibility that this could be non-zero is if I plus 1 equal to j, right? Just look at that. I mean, if I is less than j, certainly Kronecker delta ij is 0, and Kronecker delta of I with j plus 1 is 0. So this doesn't contribute. Only possibility is this might contribute, right? But this can only contribute if one of these two guys is I plus 1. This cannot be I plus 1 because if so, j would be I, but we are saying j is greater than I. The only possibility, therefore, is I plus 1 equal to j. Right? That's the only time. And then the answer is minus, because that you see the signs are coming with these signs. Okay. So the conclusion there is, so let's write it like this. So let me call alpha 1, so the roots. I mean the simple roots, I'll call alpha, labeled by alpha I, which is nothing else but omega I minus omega I plus 1. So I label the roots like this, the simple roots like this. So alpha 1 is omega 1 minus omega 2. Alpha 2 is omega 2 minus omega 3. So I just give it some notation. It's a notation. And for each of them, let me go to the Dinkin diagram. Dinkin diagram, no? You remember the rule was that for every simple root, you put a dot. Or a dot. So there are n minus 1 dots here. Right? Because total number is n minus 1. N minus 1 simple roots. This is alpha 1, this is alpha 2, alpha 3, etc. Length square are all equal. But the dot product is only non-vanishing between alpha 1 and alpha 2 and alpha 3. Right? And that's simply minus 1. I mean, it's so it's only one line. So you connect like this, that, like that, like that, it goes on. This is what we're calling a(n minus 1). The Dinkin diagram, the series a(n minus 1). Okay, because n minus 1 dots are here. So this way we reproduce the one infinite series of the Dinkin diagram, no? A(n) series. So yeah, what's the time now? Sorry, 5:30. Okay. Okay, so this was just the first part. Now the point is to go through the remaining ones. That was the A. Now, if you, then the other examples which are SO2N. Once again, you go through the analysis in this chapter, in this page 90, 91, 92, etc. Okay, section, chapter 13. 13.3, that's for SO2N. And 13.4 is SO2N plus 1. And then finally SPN. So in all of these things, okay, what I want you to go through is, not now, of course, after the RQM exam. Basically, you go through this chapter. So sections. So what are the sections? Here. Yeah. So first of all, the chapter 13. So chapter 13. So 13.3, section 13.3. This is for the SO2N. And 13.4, I think. Yeah, 13.4 for SO2N plus 1. And 13.5 for SPN. And so this was 13, but for each of them, so in this because in chapter 13 we didn't introduce a concept of simple roots and so on, right? We didn't introduce. So in chapter 14, then you can, given using this information, you can go to the chapter 14, and we already did the AN series. So there is a page. So this guy is in the page. It is actually titled DM SO2N plus 1. And CN, this was the CN. So this is in page 102. And CN, which is SPN. And there is the DN is probably the next page. Yeah, the DN is actually the DN is the next page. DN series. DN series, the SO2. So this is in page 103. So these things, try to go through that. But the idea is the same idea. So the steps are essentially that. So in this chapter, you just construct all the non-zero roots and the inner products between non-zero roots, like here. By first going from using the Cartan killing, you have the roots, you find what are the maps to the Cartan and the generators. Each root is mapped to a certain Cartan generator. And using that, you can determine the inner products for all of this. Now, in the chapter 14, then you specialize to the case of simple roots. First find the simple roots, and then specialize to the simple roots. Because all these Dinkin diagrams are just given by the simple roots, inner products between the different roots. And from that, you can identify these diagrams. So that's the thing. And go through that and see if you have any questions, we can discuss that on the next week. But do we have any time to do the spinner? Okay, I don't know. It's a pity though not to talk about the spinner representation, because it is so crucial. You know that they edited that in RQM, right? That spinors are 4-component objects in 4 dimensions. Now the question is, can you determine it purely from this algebraic approach? Okay, there you constructed the matrices. Gamma mu, anti-commutator was proportional to G mu, right? By A times mu. And from that, you constructed the gamma mu's, and that is what it turns out that the gamma mu's are 4 by 4 matrices. Right? But how do you, so suppose I'm just looking at some arbitrary dimension. How can I construct, to construct gamma matrices, first of all, you need to know what matrix I should be looking at. What, how many number of columns and how many number of rows and so on. So for that, so this is a systematic way to approach this question to determine what's the dimension of the spinor representation, which means the gamma matrix should be what matrix? Not in 4-dimensional is 4 by 4. No? In 6-dimensional is something else. In 10-dimensional is something else, and so on and so forth. No? So how do you systematically determine that? Purely from algebraic approach. Nothing, you don't need to do this. So this was the idea, but I think now we should maybe should stop. I don't know. I mean, if Wednesday we get some time, I can just mention. This will not take much time, 15 minutes or something, half an hour. Half an hour. So, any questions?
I have a question here. There was this part to try to know if the basis of the dual of the root space is orthogonal. Then we have to make
Basis of the dual spaces
is orthogonal, are orthogonal to each other. We have to make sure that each omega I is a root, right? Or
okay, yeah. Here you see this. This is not orthogonal at all, right?
yes.
Because omega I, if omega I was in this space, then it will be orthogonal because omega I dot omega j is delta j, right? But omega I themselves are not in the H star. They are in the V star. I mean, but not in the H star. So, that's but in none of the other cases it happens. In other cases, you really have a good. You can choose a orthogonal basis already in the H star. Here, unfortunately, you cannot. Because of this constraint, caseless constraint. That's what makes the difference.
Question, Professor. The automorphism can be a non-linear mapping.
So, repeat that again.
The automorphism.
O2.
Automorphism is it?
Automorphism. No, automorphism is always like a auto. It's auto. Yeah. So it will be automorphism from vector space to other vector space will be in the same dimension vector space. It will not be in different dimensions. So if you take a square, quadratic, like an inner product, that will be one dimension. It will be just a number from some n-dimensional vector space to a number. So automorphism will have to first of all preserve all your structure of the space, whatever your space is. So if you're talking about automorphism between vector space, it should preserve the vector space structure, which means linearity. Vector space structure is all linear, concept of linear addition. So, but I mean, if you're talking about the automorphism of groups, the groups are not vector spaces, right? But then, so from one group to another group, in that case, what you have to preserve. So if suppose G is mapped to some G prime in another group, let's say, and H is mapped to H prime, then G composition H should be mapped to G prime composition H prime with the composition rules, corresponding composition rules. But here it's a vector space, in the level of infinitesimal generators. Okay. So, anything else? Any questions from here? I think you don't have a tutorial to see, right?
So the will be the next one day.
Yeah, because of the arcade exam, so I think you're now going to focus there. But so Monday you have that.
Tuesday.
Tuesday.
Monday is holiday.
Yeah, Monday is holiday. Yeah. Unfortunately, not for you. You'll be studying. Yeah, I think that now, after that, you don't have any break, right? You go straight to the
3 days, 2.5 days. We just need to sleep. I'm taking all sleep.
I think that you now wait until the Christmas holidays.
Yes. Sounds so crucial. Say it out loud.
Tough, yeah.
But it seems kind of fun. It is interesting.
Yeah. I mean, it's because I mean, I assume that all of you want to continue doing research. No? That is the main thing. So it's not the exam which is important. The exam is okay, fine. You need to get good grades to get, PhD positions and so on, because they look at the record wherever you apply. That is true. But the ultimate aim is to do research. And to do research, you really need to understand in depth. Some things. Yeah. Okay.
Looks like 5 weeks aren't enough to go into.
5 weeks?
5 weeks are too little to go into the depth with.
Yeah, it's a problem that I know. I mean, yeah. You see, in the old times, we used to have, maybe no point in recording this now. Yeah, old times meaning even just 5-6 years back. What we used to have is in the first semester, there will be 4 courses. They all start more or less at the same time and go on up till end of December, before the Christmas. So there was more time to digest it, because I mean, many of these are new concepts, right? So it takes a while to digest. I think to get used to that. So that is a problem. But the disadvantage with that was that the knowledge that you, for example, in particles course, he'll be doing now afterwards. Alexei will be using a lot of this, the knowledge that you already got from, for example, the fermions, RQM, the features of all these the groups, the representations of the groups, and so on. Okay, not just SU2 and SU3 perhaps. SU2 and SU3. And the discrete symmetries, the parity, the transformations, and so on and so forth. So these are kind of needed. That's the reason. So then we thought maybe 5-6 years back that perhaps we should finish these 2 courses because these are needed for other courses. But I realized this problem because I mean, this is the first time I think when you are exposed to this, the algebras and so on. Okay, you have seen SU2, SO3, you have seen in the quantum mechanics course. But maybe not even really calling it, you have seen the harmonics, spherical harmonics and so on and so forth. So that you are familiar with. But SU3, etc., you're not familiar with at all, right? So you're like the first time you're seeing these things. And it takes a while to sink in. It takes a while. Because it's one thing to be able to do some calculation. It's another thing that it becomes part of your thinking. That requires time. So this is a disadvantage. So I don't know. You need these things for the other courses. That was a reason for change. Okay, so then see you. Good luck with the RQM, and then we'll meet again.